This 5 and this 2, I'm going to bring them out in front. And actually, for the first time, I'm going to bring it in front of the integral sign because it's just going to carry. Constants can come out. You can never pull variables out, ever. All right? Constants can come out. And what do I still have in here? 1 over 1 plus u squared du. Okay? And what? That's the antiderivative of this is arctangent of u. 5/2 arctangent of u plus c. But what's u? Because we're not done here. X squared. 5/2 arctangent of x squared plus c. And you could always check it by taking its derivative. Okay, so I have a question for you. What made you do that?
I just saw the 1 plus x.
So you just saw this and started thinking arctangent?
Mm-hmm.
Had you ever seen that before?
Yes.
You had seen it? Okay. Thank you for being honest. Okay, most people aren't going to see this, all right? But now you have. And now you need to now you know you have to kind of think that way. You just have to think that way. Even though that having a 1 plus x squared here would have been arctan. It should have been something we were thinking of. But the x to the 4th is not automatically arctan. And in fact, if that was x cubed, no way, it's not happening, all right? So this is kind of a trick, right? I mean, it's like Cal 1 is like teaching someone how to drive a car. You know, it's just like procedures and steps, right? Turn the wheel, car goes that way, turn right, step on gas pedal. Cal 1. Cal 2 is like almost magician-ish, you know, pulling rabbits out of a hat. And that's what makes it hard to teach, because it's hard to teach that intuition. It's why it's better if you're really good going and doing the Cal 1 part, right? If you're comfortable with all the chain rule and all that, it's just easier to see things backwards. Okay, that was a good problem, right? That was a good problem. How about this one? Almost the same problem, right? Almost the same problem. Yeah? Any ideas here? Batter up. Okay, so what do you want? What do you want as your u? What do you want as your... Same thing? So you want u to be x squared? Why? So what is substitution? The whole idea behind substitution is you're supposed to look at this, you're supposed to see something in its derivative, right? It's okay to be off by a constant, but that derivative can't be trapped.
Can you do the denominator thing?
Do the whole denominator? Okay, if I let u be the whole denominator, the derivative of that is what?
Well, it's going to be
What's the derivative of the whole denominator? 4x cubed? X cubed? You're off by a constant? We're in business. Yep.
But then I thought can't be in the denominator.
U can be in the derivative can't be. So we're going to let U be 1 plus. See, so that's why you have to look at each problem is unique. Just because we have the same format down here doesn't mean we're going to have the same approach. The derivative of that's right there. It's just we're off by a constant. So let U be that. Du is 4x cubed dx. So this right here is going to be our U. Right? That right there is going to be our U. Yeah. And then this piece right here, I have an x cubed dx, right? See, I'm doing this little blob around it because those really could be right next to each other, right? This x cubed could be right next to the dx. And that's, you can see it, it's right here, right? There's x cubed dx. I'm just off by 4, so I'm going to divide both sides by 4 here. So 1/4 du equals x cubed dx. And now I should be able to rewrite the whole thing. All right, so where should I start here? I have a u here, right? But it's on the bottom, so I have 1 over it, right? 1 over u times x cubed dx, which is 1/4 du. I'm going to pull the 1/4 out now, starting to do this every time. Do you know what the antiderivative of 1 over u is? The natural log. Okay? So this is going to be 1/4 the natural log of the absolute value of u. Remember that last class I said anytime you do the antiderivative of 1 over x, you get natural log of x. So the antiderivative of 1 over u is natural log of u. But what is u? X to the 4th plus 1, or you could do it the other way around. And how would we check the answer? Take the derivative, right? So that is good news in Cal 2s. You can always check your answer. Like, so if you're taking a test and you get an answer, you're like, I wonder if this is right. Just take its derivative. You better get back the integrand, right? If you get back the integrand, you're good. But you have to be able to take the derivative, right? So. Interesting. Okay. So how do you get good at this? You do every problem in the book in this section. You try and do every problem. All right? The first few problems in this section, the first 6 problems, they tell you what u is. They give you an integral, they say, hey, let u be this, and then you carry it on the rest of the way. After that, problems 7 through 52, they don't tell you what u is. And I recommend that you do every single one of these. I mean, that's my recommendation to you going into Cal 2. Because the way Cal 2 works, I mean, it's kind of like Cal 1 in the sense that if you can't take a derivative, like can't do product rule, you're never going to do well with quotient rule or chain rule. In Cal 2, if you can't do U substitution, you won't be able to do the other techniques. In fact, the other problems that you do later, you're like going to get the problems down to U substitution. So you have to like chip away at it, and then you're like, oh, I can just do that with U sub, and this one over here I can do with this, and so you'll have this like one problem that turns into like 4 different problems, if that makes sense. All right, how about this one? What's that? Say that again?
That's an inverse sine.
Yeah. So are you recognizing that the fact that you have square root of 1 plus x squared on the bottom, that's the derivative of arcsine, isn't it?
Right.
That's the derivative of arcsine. So maybe that has something to do with it. If you take derivative of arcsine of x you get 1 over the square root of 1 plus x squared, right? That right? Minus, it's minus, hold on. It's minus, so no, it's not going to work. But the fact that like those neurons fired in your brain is a good thing. All right? That's a good thing because that's the way you want to be thinking. You want to be like, this may be something to do with arcsine.
What about the hyperbolic?
It could be, but we haven't talked about hyperbolic functions. So for that reason, it's off the table. Well, should I check my text messages again or surf the web? So I really think that this has a lot to do with what we're going through here. There's a lot to be said about the type of person you are, like some people will get to this Cal 2 and they'll get to this sort of thing and they'll just be like, look, I tried something, it's not working, and I just don't like this. And other people are like, I'm gonna get this. I'm gonna get it. I'm gonna win, and they're just determined. It's just this persistence, and you have to be persistent. You have to. And I think that's part of why you have to take Cal 2 to become, for these different degree plans. It's not that you're ever going to be integrating, but are you this type of person that faces a problem and continues to throw yourself into it until you break through or not? Right? I mean, that's what you need to do, whatever, computer science. You can't be like, I can't code it, forget it, man. You have to be like, I'm going to get this, I'm going to stay up till 5 o'clock in the morning, I'm going to get this, right? I can still remember when I was in Cal 2, laying on my apartment floor at like 3 in the morning doing these problems, trying different substitutions, All right, who's going to take a swing? Al?
I would just take the denominator and make the substitution. Yeah, exactly.
The whole denominator? Like with the root or without?
What's inside the...
Just in the root? Okay, so I'm going to do that. Why would we not do the whole root? Like, why not do this? Why not let u be equal to square root of 1 plus x squared? Why is that probably not a good idea? Because the derivative of this is nasty. It's 1 over 2 square roots of this times 2x. So let me just write it down. The derivative of this would be 1 over 2 square roots of 1 plus x squared times 2x. Yeah, the 2's cancel, but do I have this sitting somewhere? No, because this is already accounted for, isn't it? This is already u, right? That's already u. So all you have left is x cubed dx. And all that crap's not sitting here, right? I mean, it's like Al said, let's take the denominator. You meant inside here, but it's like if you take too much, it's not going to work. If you take not enough, it's not going to work. If you make the wrong substitution, it's not going to work. You have to make the correct substitution. And I should also say that the problem has to be made so it'll work, okay? And like this problem, if I just go and like close my eyes and reach into the bucket of integrals and just throw it up here, chances you can solve it are like 0 essentially. So these are like specially tailor-made just to be solvable.
You mean like chances we can solve it or like chances you can solve it?
I couldn't solve it either. Like it turns out that if you were to take like the bucket of all integrals, okay, so this would be the space of all integrable functions, all right? And you randomly pick one out. The chances that the probability that you could integrate that using techniques of integration that you learn in calculus is 0. All right? However, in Chapter 8 in Calculus 2, we cover what are called Taylor and Maclaurin series. And what we discover there is that there is a way to integrate them using an approximation. And then, so like we can get the answer, but the problem with the approximation is that it's an approximation, but we can make it as close to the true answer as you ever want it to be. And that's good enough for the real world. Because if you're building, I always make the analogy in Cal 2, even though it's an approximation, if we can make it as good as we want, then if I'm manufacturing tricycles and I'm manufacturing the little ball bearings for the tricycle wheels, like I don't have to be very accurate with that, right? It's a tricycle wheel. Who cares, right? If it stops turning, it stops turning. They go get a new tricycle, right? So I could approximate and be happy with very, very relaxed tolerances on those bearings. Now, if I'm building an aircraft engine, right? Turbines and stuff, those bearings have to be precise to the, thousandths, 10,000ths of an inch. Well, so then can we approximate? Yes, we can, because we can get it as precise as our machine is even capable of being. So to answer the final question is, if we reach in and grab one, the probability we can integrate it is 100%, so long as you have power series from chapter 8. Yeah. Okay, back to this. So, what was u going to be? 1 plus x squared? Okay. Sometimes you just have to swing. Like, it's just close your eyes and swing, all right? And just hope for the best and see. And you'll learn more that way, all right? All right, so if we do that, we have no choice but to make du 2x dx, right? So I'm going to be able to replace this down here with u. And now I've got a problem, right? Because I've got x dx here with the 2. The 2 doesn't matter. I can always divide by 2. But up there I've got x cubed dx, right? Can you do what?
Use one of the x's.
Let's use one of the x's. Good job. Good job. What made you think that?
I don't know.
I don't know either, right? Is that still the same? Just peeled one of these x's off, right? Is that legal? That's legal, right? Okay, so now we're getting somewhere. This x dx matches up with this x dx. And we already said that this 1 plus x squared under the root is going to be replaced with u, right? We are off a little bit here, aren't we, with this 2? This 2? So I'm just going to go like this. 2 gone, 1/2 here. Is that all right? So this will be replaced with u. So we'll have square root of u down here. This will be replaced with 1/2 du. The only issue is this x squared. And that's a problem because it still has x's in it, right? However, look at this. This is our relationship between u and x squared, isn't it? Doesn't this have x squared in it? So could I solve this equation for x squared? What would it be? U minus 1. U minus 1 is x squared. Wow. So that means that I can replace x squared with u minus 1. Right? This is weird. This is weird. Okay, integral. X squared is going to be replaced with, yeah, I think I've got, yeah, that's my x squared. So x squared is being replaced with what? U minus 1. On the bottom I have square root of u. And then this right here becomes 1/2 du. And even though that looks bad, it's not. 1/2 is going to come out. Now watch. What am I doing here? Splitting it up, right? I've got 2 terms on top, 1 on the bottom. So I'm going to split it. And those are all powers of u, aren't they? So before I do any more, I'm going to write 1/2 integral. This will be u to the half minus u to the negative half du. So that's just using the fact that this is u to the first power over u to the 1/2. So u to the 1 over u to the half is u to the half. You subtract the exponents. Here, just bring this u to the 1/2 up and make it u to the negative 1/2. Yeah. Okay, 1/2 is here. Now I'm going to do the antiderivative of each of these, and I'm going to have to do the power rule for each one of these. And the 1/2 is just going to sit out in front. So I'm going to put a bracket here, even though I could use a parenthesis, but I'm going to use a bracket. The antiderivative of this, so we have to add 1 to this power. So 3/2, and out in front is 1 over 3/2, which is 2/3. 1 over 3/2, so 2/3 out here. I'm hoping you did your homework. Okay, like that. That's the antiderivative of this. And then here we have to add 1 to this. Negative 1/2 plus 1 is 1/2. So we have minus 1 over 1/2, which becomes 2u to the 1/2. And then don't forget plus c. We're almost there. This is almost fun. All right, I'm just going to distribute the 1/2 through. And at the same time I do that, so this times this is going to, the 2's are going to cancel. I get 1/3. What was u? 1 plus x to the 4th? Or 1 plus x squared. So it's 1 plus x squared to the 3/2. And then minus, let's see, 1/2 times negative 2 is going to go away. So this is going to be 1 plus x squared to the 1/2 power, right? With square root. Agree? Plus c. There it is. There's our antiderivative. Do you all believe that that's the antiderivative? Do you believe it is? How could we check it? We can take. I'm going to do that real quick. So you ready? Check it real fast. Take derivative of this. 3/2 comes out, hits that. The 3 and the 3 cancel. I get 1/2. 1 plus x squared raised to, I have to subtract 1 from that. 1/2 times chain rule, derivative of what's inside, 2x. Minus 1/2 comes out. 1/2. 1 plus x squared. Subtract 1. Minus 1/2 times derivative of what's inside, 2x. 2's cancel. 1/2, 2, 1/2. All right, where are we? We have x square root of 1 plus x squared minus x over square root of 1 plus x squared. Okay, so I wrote this as a square root of 1 plus x squared times x. And then this one, because it was a negative exponent, dropped it down, and I left that x up there. Not the same. Common denominator. Okay? So let's get a common denominator between these two. So I put a root 1 plus x squared here. I put a root 1 plus x squared here, right? And when I do that and put them together, let's see what we get. What does this numerator become when I put those together? It's x times, those two together become 1 plus x squared, right? And then I have minus just x, and that's all over my common denominator, which is square root of 1 plus x squared. And now let's distribute here and here. So we get x plus x cubed minus x over square root of 1 plus x squared. X is canceled. X cubed over that. It works. That was fun. So Al, you said 1 plus x squared, right? It worked. And then you did the pulling. That peeling off of that x was like the key move to the problem. That seeing that x cubed could be that x out there. All right. Let's go back to the first problem I put on the board. Sometimes the easiest problems are the hardest to understand. So do y'all remember what I said the answer to that would be? 1/3 sine of 3x, right? Plus c. All right. I'm going to make a substitution. What's my substitution going to be? Do I see something in its derivative? What's the derivative of that? 3. Do I have a 3? I have a 1, right? I have a 1, so I'm off by 3. So u is 3x, du is 3 dx, right? And now I can multiply both sides by a third. And so anywhere I see 3x, it'll be replaced with u. And anywhere I see just dx, right? It'll be replaced with 1/3 du. So this now becomes cosine u times dx, which is 1/3 du. And I think from there you can probably take it, right? 1/3 sine of u plus c, but then replace u with 3x. So this problem is done with basic u sub. Yes?
You said there's like 5 other methods to go about solving this.
Antiderivatives.
You can use all the other 5 to solve this?
No. The other 5 are designed for harder problems.
Okay.
So it's like you'll get a problem where u substitution won't work. I'll put one up here just so you can see it. There. So there's no u substitution that you're going to do, that you'll be able to do here. It's just not going to work. Okay? You can sit there, you can play with it all day. You can play with it for the rest of your life and you won't be able to get it, all right? And there are some integrals, like I said, that you just can't find the antiderivative no matter what, unless we have power series from chapter 8. Like that one right there, this one has a technique to get this one. We use integration by parts. We have to utilize that technique 2 times in a row to get this. This one, no go. There's just no way. In fact, that's going to be on my test. That's going to be on my final exam for my Cal 2 class. So they're going to have to convert that to a power series first, and then they're going to have to do the power series, find the antiderivative of the power series, and then work it out. So.
What makes it so difficult? Is it the E or is it the combination?
It's just the combination. I mean, if that was just e to the x, the antiderivative would just be e to the x, right? But it's that x squared causes major issues. Okay, we still have a little bit of time, and of course I'm never going to run out of problems that I could show you, right? So let's see here. How about this one?
What is a definite integral?
We'll talk about that. Okay, how about that? We're going to talk about it today because I have to tell you something before you go try your homework. All right, so we did one like this last class. If you look right now, there's no real clear indication of what your substitution should be. You could let u be x, right? But we said don't ever let u be x. But how about just this 2 plus x? Let's try that. Let's see what would happen. If we let u be 2 plus x, what's the derivative of that? Just dx, or 1 dx, right? So I can replace 2 plus x with u. I can replace dx with du, and the only thing I need to account for is that x out front. Yeah, but I can do this again and solve this. U minus 2 equals x, right? So this right here and that. So when I rewrite this, I get u minus 2, that's x, but then times what? U to the 10th, and then dx, which is du. Now, did that make it any better? What's the big difference between these two? Yeah, the power here is just on u. Here the power was on a binomial. So the only way to go about trying to do that without any technique is to expand that binomial. 2 plus x 10 times. Here, we can just distribute that through, right? So we get u to the 11th minus 2u to the 10th du. Distribute. And then I can do these individually, right? Because they're separated by subtraction. So the antiderivative of that is 1/12 u to the 12th minus 2/11 u to the 11 plus c. That's just power rule on each of those terms. And I do have one more step, right? Have to replace u with 2 plus x. That's a good example of one where you make a substitution that doesn't look like it's going to get you anywhere, but it actually gets you there. Any questions on that? Okay. So let me wrap up today here with kind of a summary here. We have this idea. This right here is the new notation, right? And this is called the indefinite integral. It's the indefinite integral. And the reason, when we do this, what is our answer? When we're asked to find the antiderivative of a function, our answer is a family of functions, right? It's this function plus c. And we said c could be anything. So I showed you a picture last time. It's this entire family. They all look the same, have the same shape. It's just move them up and down vertically. So we say indefinite because, yes, you get an answer, but you're not definite which one it is because it's an entire family, right? That's the way you kind of think of it. Now, we compare that to this, which we have not talked about, but that's what we'll do next class. And that's if we take that same notation, and what we do is we put a number here and a number here. This is called the definite integral. So remember, for this, the answer is going to be a family of functions. Right? Your answer is a family of functions. For here, your answer is going to usually be a number. It is possible to get infinity there, but. And here, I think we had some idea that it's this family of functions. We could kind of visualize that. Here, this number, what it means, right? The meaning of that number is what we're going to talk about next class, is if we take this function and we look at a function, this function f, on this little interval, then the number that comes out of this is representative of the area of that. Okay? That's what it is. So the area below this curve down to the x-axis, that area underneath that function is what we get when we do the definite integral. Now, I haven't shown you how to do it or anything like that, and that's what we'll do next class. So for your homework, what I think you should do on your homework thing, is there a homework assignment for 5.5? Yes?
5.3.
There's not one for 5.5? There's not one for 5.5? Okay, so I'm going to say for 5.3 you should not mess with yet. Wait, hold on. 5.3 was last time.
No,
No.
No, 5, 4,
4. 5-3 is next time. Okay. So what I recommend you do is 5-5. Okay. I think you should probably try. Now this is like you're going to go to Cal 2, right? Okay. If you're going to Cal 2, I recommend that you go and try and do 1 through 52. Now tonight, don't go do all these. Okay. I'm just saying, like before you walk into Cal 2, you should feel very comfortable with these. Now in my Cal 2 classes, I start as if you've never seen an integral sign in your life. So I start over from scratch because everyone comes at different places. But if you want to be ahead of the game, then I would recommend you do that. Now, I think I have a video for this, but I don't know if it's on your homework solution video playlist. So I'll put it on there, okay? That way you can see my homework solutions for this. And then next class we will, sorry, I forgot. If you 5-5 is on the homework solutions. Okay, so when you're doing this homework, some of the problems are going to have numbers. Okay? Right? They're going to have numbers. Just ignore the numbers. Okay? So like for example, there's a problem here that says, let's see. There it is. There's the problem. So they're using t instead of x. Just act like this isn't here, all right? And just go try and find the antiderivative of that. Now, if you check your answers in the back of the book, they're not going to match. So that's why you should look at my homework solution videos, because I'll actually work through it and you'll see the antiderivative in there, all right? All right, next class we will do definite integrals, fundamental theorem of calculus, and we'll be done, all right? Yes, sir. Let me turn off my camera first. 5-3's not on there?
Yeah, 5-3 is not on there.
I think I have another video that has like